Hello, we are Purdue SoCET students on the AccuSemi Standard Cell Library team. Our team is composed of Tsai-Shuang Lan, Kerway Tsai, myself, Andrew Schlabach, Tam Lee, and Yiyun Wang. Our GTA advisors are Boyuan Chen and Sutton Hathorn, and our faculty advisors are Dr. Mark Johnson, Dr. Wei Zakharov, and Dr. Sergey Zakharov. Our PDK is being developed for use with the OpenLane design flow. OpenLane is a tool which packages together a variety of open source tools in a way that is easier to use. This is composed of 4 main steps, but this list is not exhaustive. At times, these are all going on simultaneously. The beginning stage is RTL synthesis. This takes your Verilog code and converts it into a tree of standard cells which can be produced on the chip. Then it goes into floor planning and routing, where it takes that netlist tree of cells and places them down in a way that they can be connected with minimal propagation delay. Then, in routing, the wires are added to the design to connect the inputs and outputs in the same manner as the netlist, so that the logic is reproduced and all the cells are wired together. Finally, in sign-off, it verifies the logic of the finished design against the logic from the netlist that was generated in RTL synthesis and makes sure that the logic stayed consistent throughout.
We will go over a standard cell library definition. So a standard cell library means a collection of well-defined and pre-characterized logic cells with multi-drive strength and multi-threshold voltage. A minimal standard cell library consists of an inverter, a 2-input gate, and a flip-flop. However, in reality, a standard cell library consists of more gates than that. With more options in the library, the synthesis tools have more flexibility in choosing the optimized gates so that the overall gate count of the circuit is reduced, thus improving the delay and saving area. Cells with different drive strengths differ in transistor sizing. The more the width of the cell's transistors, the more the drive strength.
In order to develop the standard cell library, we first need schematics for all basic logic gates we plan to include in the library. For our project, we are using the open source schematic circuit editor XSchem. On the left-hand side, you can see the basic NMOS and PMOS symbols in XSchem. Because AccuSemi uses an 800 nanometer NWEL CMOS process, all of our NMOS and PMOS FETs will have an 800 nanometer length. We are still working on finalizing the sizing for the MOSFETs, but the general idea is for PMOSes to be double the size of NMOSes so that the rise time and fall time of the gates as well as the resistance of each MOSFET will be equal. I have examples of our inverter schematic and NAND gate schematic shown on the screen. To test each schematic, we ran simulations on XSchem using ngSpice as our simulator. For the simulations, because our current version of ngSpice does not support level 7 MOS spice models, which were provided, we are using MOS level 2 spice models for simulation. I have not included all of our simulations here, just the inverter simulations to demonstrate functionality. First, we have the DC simulation, where a voltage sweep from 0 to 1.8 volts was performed and the output voltage was measured. In the plot, the yellow line represents the output voltage and the blue represents input voltage. As you can see, the inverter works properly as the output transitions from high to low as the input reaches the threshold voltage for the NMOS to turn on. In the transient analysis, the same functionality is observed in a better waveform.
The next step is layout. IC layout, also known as IC max design, is a representation of an IC in terms of planar geometric shapes which correspond to the patterns of all semiconductor layers that make up the components of the IC. Here we are using 800 nanometer process provided by AccuSemi as a guideline for our layout. Also, in the standard cell library, to reduce the amount of extra routing, a more standard looking layout of each cell is preferred. For example, we set all of the cells with the same height so that we can combine cells more easily. Here we have a term called tract, which can be related to length, and pitch is the minimum distance between two tracks. So, with the consideration of using only 2 metal layers, using 12 tracks in pitch, the height of all standard cells is set with the same 45 micrometer. Let's use a 2-input AND gate layout as an example. 2-input AND gate is made by NAND gate plus an inverter. So the left is a NAND and the right is an inverter. We can see that it has a height of 55 micrometer and all layers here are marked in different colors and shaped. So to verify the layout is correct, we have to run DRC and LVS checks. DRC stands for Design Rule Check. This is to ensure that the width, spacing, enclosure, and others on each layout meet the specification, so that the polygons in the layout can be manufactured as drawn. For example, the minimum width of metal 1 is 1.1 micrometer, and the minimum spacing between two metals is also 1.1 micrometer. Next, LVS stands for layout versus schematic. This is to confirm the layout matches the schematic by comparing the original netlist and the netlist generated from the layout, so that we have the correct circuit.
To finish characterizing a standard cell library consisting of NAND, NOR, SOR, AND, OR, XNOR, inverter, and D flip-flop gates. This goal includes having the correct simulation result to verify the functionality of the gates we designed. We will need to produce a DRC in LVS screen layout, and we will need to agree on the number of tracks for the cell's height, since all cells need to have the same height. Finally, we need to have cells with multi-drive strength. We can be obtained by adjusting the transistor's width. This is the end of our project presentation. Thank you for listening.